All right, hello and welcome to the second part of lesson 7.6. In this video, we're going to do some applications of rational equations. The primary intent behind this video is to model and demonstrate to you how do you break up a word problem, how do you interpret and analyze the situation, and how do you construct ratios, equations of ratios, to represent what's happening in the problem. As far as solving goes, I'm going to do that really quick in this video. The last video was primarily focused around solving. I'm going to spend more time talking about how do you analyze the problem and how do you create the equation, okay? So, as it says kind of right here, give careful thought about your variables and pay attention to what the question's asking, right? So there's a multitude of variables that could be at play here, right? Example, the train speed versus the bus speed. And maybe the question wants the bus speed, but maybe the train speed is X, and maybe the bus speed is X plus 20, right? And so then you'd say, oh, well, if you found X, but the question asks, what's X plus 20? Well, then you would need to figure out what that is, yeah? I think as we go, maybe you'll see what I'm talking about. But just really make sure you read the question, read what it's asking for, and just think carefully about the variables at play here, okay? Very good thing to name your variables. Okay, so in this we have two kinds of problems. The first is what's called a work rate problem. The other is called uniform motion, but I'll get to that when we get there. What is a work rate problem? Okay, well, the premise of work rate, this is also called combined rates. You could Google this also if this video isn't enough, okay? Work rate problems are the idea that some person or some entity is accomplishing or fulfilling a task within a certain amount of time, right? So for example, I don't know, machine A can produce, right? So machine A can produce 15 parts in 1 minute, right? But machine B can produce 10 parts in 1 minute. Then the question might be, how long would it take them to produce 60 parts if both machines are working, right? So what the thing is so machine A and machine B are both doing the same task. Now they're doing it at different rates, but if you can, there's a way to add those rates together because they combine into a single rate because they're working to the same goal, because they're accomplishing the same task, yeah? The fractions are able to be added and the rate combines, okay? So that's an example of what we're talking about. But what's really important and the main takeaway here is the equations you're using, the fractions you're using are task over time. Students forget this a lot. They forget that, one, it's a fraction, and two, what is the task? What is getting fulfilled? What is being done in this amount of time? Okay, so just think about that carefully. Okay, so let's walk through this example. This is a classic example. Catherine can paint a house in 15 hours. Dan can paint it in 30 hours. How long will it take both of them to paint the house if they work together, right? Assuming it's the same kind of house, right? Assuming we're working on, I don't know, ticky-tacky houses where every single house is the same and they always paint at the same rate, which is a very, very ideal and unrealistic scenario, but just humor me, yeah? Humor me. Say that they could do this, right? So Catherine can paint a house in 15 hours. That means Catherine's rate is painting one house per 15 hours. That's Catherine's rate of painting. Dan can do the same thing. He can paint one house in 30 hours, right? So notice that it didn't say Catherine can paint 3 houses in 15 hours. It just said a house. The fact, it doesn't say one house. You have to know that a house means one house, which seems kind of obvious, but it's still something to think about, right? Okay, so those are their 2 rates. And the thing is since they're doing the same goal, they're working to the same task, you can add these rates and they combine. So they equal some new combined rate. Well, within that rate, what is their goal? Their goal is to paint 1 house together. And by the way, just because of this problem, this just so happens that these are all 1s. They're not always going to be all 1s, but they could be, okay? Because it could ask, how long does it take them to paint 5 houses? In which case, those would be 1s, but then this would be a 5, okay? Then how long does it take them to do that? Well, I don't know, so that's what I call X. It takes them X hours together. So, clean this up a little bit. Excuse me. 1 over 15 plus 1 over 30 is 1 over X. And just like we did in the last video, identify the LCD and multiply to eliminate all the fractions. In this case, the least common denominator is going to be 30x, so we're just going to multiply by 30x through and through. You can go ahead and do that. You should end up with 2x plus x is 30. That yields 3x equals 30, which means x is 10. 10 what, you might say? 10 hours. Thus, the problem is solved because x represents how long it takes for them to paint 1 house together. It would take them 10 hours. Yeah? And that's it. That's a combined rate problem. But I'll let you know that this is one of the simpler ones. It's just to get, and introduce you to that idea. Okay? All right. Let's go to example 2. It's called uniform motion problems. Now, these are a little bit trickier, okay? This is a lot more involved and a lot more variables to think about and consider. Also, when doing these kinds of problems, it's not really the same setup every time. When it comes to work rate, it's always adding or subtracting rates because things either work together on the same task or one thing does one task and the other does another. By the way, if you're saying, what does he mean by that? I said, well, remember my machines? Well, machine A could make 15 parts per hour, but machine B could destroy 10 parts per hour. Which, why would we be doing that? I don't know. But then that would mean that their rates would be subtracted there. Yeah. So you have to think about whether it's plus or whether it's minus. Okay. But the thing about uniform motion problems, they're all using speed is distance over time. So you have to use that fact to help set up the ratios. Thing is, you don't really add speeds, right? Example, the bus and train, I think I mentioned earlier, bus and train. Maybe a bus goes 30 miles an hour and maybe the train goes 70 miles an hour. Does it make sense to add those rates to find a total speed? Right? Well, no, because they're 2 separate objects traveling independently of one each other, right? In the other context, the rates combined because they were working towards something. When it comes to motion, you don't add speeds together because that doesn't really make sense, right? It doesn't make sense to say that, the total speed of the bus and train is 100 miles per hour. What? What does that even really mean, right? What you can add, though, is distance or time. You see, you could take the time a bus takes and add that with the time a train takes, and that would get you the total time it took for both of them to travel. And you could do the same thing with distance as well. You could say, the bus traveled this distance and the train traveled this distance, so together, between the 2 of them, they traveled some distance that's added together, right? So it does make sense to add or subtract distance and time, but not speed, okay? So that's just something you want to keep in mind. So here is our example problem that we're going to get started with. It says, Tim paddled his kayak 12 kilometers upstream against a 3 kilometer per hour current and back again in 5 hours and 20 minutes. The question is, how fast is Tim's speed in still water? So still water, that's water that's not moving. So that's like his baseline paddling speed absent of the rate of the current. You say, what, Mr. Spake? I say, look, there's the river. Here's your boat. There's you, or Tim in this case. Hello, Tim. Smile. Okay, so the current, if, it's going to flow this direction. If Tim, I guess this isn't quite a kayak. This looks more like a sailboat, but who cares? Whatever. He's in his little boat. If he paddles downstream, then his paddling speed, which is what we consider the speed in still water, gets added with the speed downstream because the current pushes him, right? It's pushing him along. But if he were to go backwards, he'd be fighting upstream, which means the speed of the current takes away from his paddling speed. Yeah? And so that is going to kind of be at play here. In a lot of problems, you're going to see this as current in water or air resistance, right? You could be in a plane. Okay, that looks more like a shark. Hello, shark. Let's try a plane. This is slightly better. Okay, with the windows, right? The wind could push against it or with it. So it could have a headwind or a tailwind pushing against or with it. So that's just to explain that aspect, okay? So let's break down what variables we know here. Let's think, because we got speed, we got distance, we got time. And we're going two directions, upstream and downstream. So I'm going to break this up. Distance upstream. I'm going to do D for distance. The distance upstream, well, it's 12 kilometers, right? And the thing is he goes back and forth. So the distance downstream is the same distance, 12 kilometers. So those two aspects are equivalent. They're the same. Okay, what else do I know? The stream of the current, or the speed of the current, is 3 kilometers an hour. So the speed of the current is 3 kilometers an hour. Well, what is his still water speed? So what I'm going to do is let x be the speed in still water, okay? Then based off that, what is his speed upstream and what is his speed downstream? Well, if you're going with the current, right, then you're going downstream. And since this current is 3 kilometers an hour and the speed he's rowing at is x, then that means downstream it's x plus 3. It's 3 kilometers an hour added to his baseline speed. But if he's going upstream, he's working against it, means the 3 kilometers an hour takes away from x, getting you x minus 3. So already what I've done is I've created some expressions representing distance and speed. The only other aspect not considered yet is time, right? Distance, speed, and time. What do I know about time? Well, I know he went upstream at some rate, and then he came back in 5 hours, 20 minutes. So that aspect, 5 hours, 20 minutes, is that his time upstream? Is that his time downstream? Well, it's both, right? It's saying that he went up and back. That means the time total is 5 hours and 20 minutes, Well, think about that. Can you make that a fraction? Because we would like these to stay in hours. Well, that's 5 hours and 60. Let's see, 20 out of 60 is a third. So that's 5 1/3 of an hour. And that means it's 16/3 hours. Okay? Because I'm just writing it as a single fraction. We're going to want these fractions. Yeah? Well, then where do I go from here? I said, well, the total time is calculated by the sum of his time up and down. I said, what? I said, look, the time he spends rowing upstream added with the time he spends rowing downstream gets you your total time. But what do you do with that? Well, the equation, again right here, speed is distance over time. S is d over t. If you can rearrange this equation and solve for t, getting you t equals distance over speed. Yeah? You achieve that by multiplying both sides by t and then dividing both sides by s. So time is actually expressed as a ratio of the distance traveled divided by how fast you were traveling. And that's information I have known and set up over here. The time upstream is the distance upstream divided by the speed upstream. The time downstream is the distance downstream divided by the speed downstream. These two times added together get you the total time. So now you can plug stuff in. The time upstream is 12 kilometers. The speed upstream is x minus 3. I'm getting that from right there. The time downstream is also 12 kilometers, or sorry, the distance downstream is also 12 kilometers. The speed downstream is x plus 3. And this equals the total time, which I wrote as a fraction, 16/3. And so that is the setup to this problem. From there, you just do algebra to solve. The hard part is setting it up, not solving it. Solving it's not too bad, especially since you get a calculator with this. Okay, I am gonna solve it. We are gonna go through it, but I just wanted you to kind of digest how that is split up. Now, when it comes to showing work for this, just to outline the expectations for tests and whatnot, do I need to see all of this? I don't need to, but if you set up this fraction wrong, it would help me if I did see this, because then that would tell me how you're breaking down the problem. Because if you set these fractions up incorrectly, but you label each piece and it's obvious to me where you were thinking, right, where you got those values and those numbers and why you plug them in, that would help me in grading. So is all this and this necessary? No. If you just start with this, that's fine, and then you could solve from there. I'll know what you're doing. But if you're a little worried, or you think, I'm not sure I set this up correctly, spend some time thinking about your variables and writing the equations. Okay? Okay. So let's solve this, and then I'm just going to breeze through this quickly because I don't want to take too much time to do it. You may notice all the numerators. You see the 12, 12, and 16. All of those constants are divisible by 4, which means you could divide the entire equation by 4 and get a simpler fraction expression. Not necessary to do, but it's going to help us a little bit. The LCD, after doing that, well, the LCD is the same either way. The LCD is 3 times x minus 3 times x plus 3. Plus 3. So if you multiply that out, in the first fraction, the 3 will multiply, the x minus 3's will cancel, and you get 3 times x plus 3. The second fraction will be the same thing, but the term that cancels is x plus 3. So it's 3 times x minus 1, or x minus 3. and then that equals 4/3 times that. The 3's cancel, and you get 4 times x plus 3, x minus 3. So that's multiplying both sides by the least common denominator. 3 times 3 is 9. So then distributing that, I get 9x plus 27. This is also 9. Distributing that, I get plus 9x minus 27 equals x plus 3, x minus 3 is x squared minus 9. That's a difference of squares, which if you distribute 4 to is 4x squared minus 36. Okay, let's clean this up a little bit. The 27s cancel, so they're opposite signs. And then this is an 18x, at which point you're going to minus this to the other side. So I'm going to get on the right side 4x squared minus 18x minus 36 set equal to 0. That's quadratic. 4, 18, and 36 are all divisible by 2, so you can cut this in half, and you can say this is 2x squared minus 9x minus 18. Okay? I'm going to, just for sake of space, I'm running out of space up here. 2x squared minus 9x minus 18. This is just a factoring problem now. Negative 36 and negative 9. I'm going to do the kickback method. I don't like it, but it's quick. And say that this is x minus 12 over 2 and x plus 3 over 2, which becomes x minus 6 and 2x plus 3. So that's the factorization. Remember that this is set equal to 0. Therefore, the roots are 6 and negative 3 over 2. Okay, so I got two answers for x, but don't just box that, right? Remember, we're in a word problem. These numbers mean something. What was x? X was the speed in still water in kilometers per hour. Does it make sense to go negative 1.5 kilometers per hour? Well, you might say yes if we were talking about velocity, but we're not. We're specifically talking about positive numbers, which is speed, so cross out the negative 3 halves. The only remaining answer is the 6. Therefore, the speed in still water is 6 kilometers per hour. And that is our answer to the problem. Thus, we're done. Okay? Notice that one was a lot more involved, a lot more extensive than example 1, right? Combined rates are usually a little bit easier because you just think about what the task is, you add them together, and you're done. When it comes to uniform motion, there's a lot more moving parts, literally moving parts, that you have to break down and analyze, okay? Also, don't forget that there was the rejection of the negative answer because that doesn't make real-world sense. So always apply your answers to the real-world context and think about what they mean. Okay, that is the premise of this video. That was a lot of content, a lot of talking, a lot of good stuff. You've got what you need if you need to go do the homework now. I am going to work through numbers 1 and 2 as additional practice, okay? But that's the lesson in sum. That's how you break these kinds of problems down. Numbers 1 and 2 are just going to be some more examples of these ideas, okay? So I'm going to start with number 1. It says Neil runs 3 miles an hour faster than Mike. Neil can run 5 miles in the same amount of time it takes Mike to run 3.75 miles. Then find Neil's speed and Mike's speed in miles per hour. There's an extension that asks to calculate their mile time, which we'll do, but I'll have you know that that's not a super major requirement for this problem. Okay? So, what do I know? Distance, time, speed. Neil runs 3 miles an hour faster than Mike. Do I know how fast Mike runs? I scan the problem? No. So, x is going to be Mike's speed. Then Neil's speed is 3 miles an hour faster than that. That means it's x, but it's 3 more than that. It's 3 miles an hour faster than x. So that handles Mike's and Neil's speed. giving it and quantifying it with a variable, okay? What do I know about their distance? Well, Neil's distance was 5 miles, and Mike's distance was 3.7 miles. 3.7 miles is the same as 3 3/4 of a mile, which comes out to 15/4 miles. Okay, that might be important. That way I have a ratio, a fraction expression here. Okay, so that handles distance and speed. The last component is time. What do I know about time? Well, this middle sentence here, Neil can run 5 miles in the same amount of time as Mike. So what this implies is we're running different distances at different rates, but we're doing it in the same time, yeah? That means Neil's time is equal to Mike's time. So then what's the equation for time? Well, it's the same as the one from up here. Time is distance over speed. So what that means is this is Neil's distance over Neil's speed equal to Mike's distance over Mike's speed. So then I just plug in some stuff here. Neil's distance is Neil's distance is 5 miles over Neil's speed is x plus 3, based off what I wrote over here. Over here is where I'm trying to point. Equal to Mike's distance. Mike ran 3.75, but we rewrote that as 15 over 4. So, you could say this is 15 over 4 over Mike's speed. We don't know, so we call it x. Now, you could leave it like this, but I'll have you know that 15/4, because it's in the top, you can do one of two things here. You can do keep, change, flip, or if you really understand how division works, the fact that it's 15 over 4 really just means that the 4 goes in the bottom, and you get a 15 here, okay? But even if you don't do that, if you just keep it as 15/4 in the top, you're going to be fine too, okay? So I'm going to multiply by the LCD, which is going to be 4x times x plus 3. I'm going to multiply both sides by this least common denominator. And the thing is the x plus 3's for the 5 term, the x plus 3's are cancel, and it'll just be 5 times 4x. That's 20x. On the other fraction, 15 over 4x, the 4x's will cancel when multiplied, and I'll be left with 15 times x plus 3. So that's 15 times x plus 3. Distributing that, you get 15x plus 45. Get the x's on one side, because this is just a simple linear equation. You should get 5x equals 45. Therefore, x is 9, if you divide both sides by 5. 9 miles per hour. Okay? And who is this? This is Mike's speed. Is 9 miles an hour. Okay? But the question is asking for both of their speeds. So Mike's is 9 miles an hour. How long is Neil's? Neil's is x plus 3, which is 3 more than 9. So then that's 12 miles per hour. And thus the problem is solved. Yeah? We found Mike and Neil's speed in miles per hour. Okay? All right. And that is that question. So, notice how this was a bit different of a setup to this one above. In this in the previous example, you had to add 2 times to total a time because you went a distance forward and back. In this example, it said that the times were equivalent. So you didn't add them, you equated them. Excuse me, yawning. And so that's, the difference there. By the way, the extension for mile time, I will talk about that just briefly. How do you find their mile time? Well, if you've taken chemistry and you know dimensional analysis, this is going to help you a little bit. Mike's speed is 9 miles per 1 hour. What is a mile time? Well, a mile time is how long does it take you to do 1 mile? That's it. I was going to say more. It's just how long does it take you to do 1 mile? 1 mile per how much time? So usually mile time's given in minutes because, you don't really want to tell if it takes you 2 hours to run a mile, you're probably not a track star, right? You're probably Mr. Spake if you are doing that. So 1 hour is worth 60 minutes, which means this ratio, 9 miles per 60 minutes, if you simplify that, if you divide both top and bottom by 3, you get 3 miles every 20 minutes. That's for Mike, right? So every 20 minutes, he's run 3 miles. But you want to figure out how long it takes to do 1 mile. So you set this equal to 1 mile per I don't know how much time. And since you want to solve for the question mark, which, you could call this something like x, 1 over x could be flipped. You can do reciprocals here and just flip the top and bottom and get 20 over 3 is x over 1, which is just x. Meaning x is 20 divided by 3, and we're going to convert that into a mile time. This is in minutes. 3 goes into 20 6 times to get 18, and then 2/3 remaining. And this is in minutes. So 2/3 of a minute is 40 seconds. So that is his mile time, 6:40. Yeah. I think I would write this. You could write it as 6:40 like that. I like to write it as 6 minutes, 40 seconds. Yeah? 6 minutes, 40 seconds. You could do the exact same thing for Neil. He does 12 miles per hour and divide this by 60. Then if you divide top and bottom by 12, that means it takes 1 mile and divide 60 by 12, you get 5 minutes. But then, of course, that just tells you exactly his mile time. He can run 1 mile in 5 minutes. That means his mile time is 5 minutes, exactly. And that's for Neil. So Neil was a little bit easier to do because it didn't have to do a little bit more. And that's their mile time. 6 minutes, 40 seconds versus 5 minutes. Okay. Will I ask you something so complicated on the test? No, I won't. Will I ask you how to find their speeds? Absolutely. Yeah. I'm not going to ask you for anyone's mile time, but I will definitely ask for speeds of stuff. Okay, last example. 2 pipes. Oh my gosh, I love the pipe problems, don't you? So what's going to happen here is 2 pipes are going to fill a pool. Now, you're going to have a large pipe fill the pool and a smaller pipe fill the pool. So obviously the larger pipe, since it's pumping more water, it's going to fill up the pool faster. But then if both pipes are running, the pool will fill up even faster with both running as opposed to only one of them running. So this is a combined rate problem because the task is to fill up a pool. So I've got 2 pipes, small and large. I know that the smaller pipe takes 4 hours longer than the larger pipe to fill one pool. So, and if I keep reading, both pipes, blah, 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 I don't get any more information on the speed of the larger pipe. Meaning, X will be time to fill pool for the large pipe. Okay? Smaller pipe takes 4 hours longer. That means X plus 4 is the time for the small pipe. Okay, so what are our rates here? Well, we're adding the rate, right? The rate of the large pipe added with the rate of the small pipe gets you the combined rate. I use C for combined there. So the large pipe, its task is 1 pool per X minutes, hours. Let's go hours per X, because you get to choose the measurement there. I'm going to go with hours. So the rate of the large one is 1 pool per X hours. The rate of the small one is also 1 pool, but it takes 4 hours more than the large pool, so I'm going to write X plus 4 in the denominator here. And this equals the combined rate. Now the combined rate, you're still trying to fill 1 pool, but how long does it take them together? Well, if I read the problem, when both pipes are open, the pool is filled in 3 hours and 45 minutes. So the time together is 3 hours, 45 minutes. Let's convert that to a fraction. That's 3 3/4 of an hour, which 3 times 4 is 12, plus 3 is 15/4 hours. Okay? So the combined rate is 1 pool per 15/4 hours. Now, clean this up so we can solve it. There's the hard part, is setting up the equation. Now you can solve it. It's 1 over x plus 1 over x plus 4 equals. Now, 1 over 15 over 4, that's like keep, change, flip. 1 over 1 times flip 15 over 4, 4 over 15. Meaning, you could simplify the right side as 4 over 15. And thus, this is the equation we seek to solve. So, my LCD is 15x, x plus 4. You need all 3 of those to multiply by. Once you do this, once you go ahead and carry out this multiplication, pause if you need to, multiply the LCD to all 3 terms, you should get the following. The x's cancel, and you're left with 1 times 15 times x plus 4, plus the x plus 4's cancel, 1 times 15x, and then on the right side of the equation equals 4 over 15 times 15 blah, 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 blah. The 15's cancel, and you get 4x, x plus 4. So let's distribute in combined-like terms. 15x plus 60 plus 15x equals 4x squared, because that distributes here. 4x times 4 is 16x. Okay, so the left side is 30x plus 60, which if you subtract that to the right side becomes 4x squared. 16 minus 30 is negative 14x. And then you subtract the constant 60 to the right side. This is all set equal to 0. Now, 4, 14, 60, all divisible by 2. So let's make the factoring easier for ourselves with smaller numbers like this. Okay? But 2, 7, and 30, they're all called what's called coprime. They don't share any more common factors. So X puzzle time. 2 times negative 30 is negative 60. The bottom term's negative 7. So what makes that work? Let you think about it. Negative 12 and positive 5. I'm gonna do kickback method for this. I do not endorse this method really, but it's effective. Okay, he's effective. X minus 12 over 2 and x plus 5 over 2. Then that is x minus 6 times 2x plus 5. Remember, this equals 0. So what are the roots? The roots are x equals 6, so that makes 0. And then 2x plus 5 minus the 5 divided by 2, that's negative 5 halves, or negative 2.5. Okay? Now, what did x represent again? X represent the time to fill the pool, with the large pipe. Can x be a negative time? No. So this negative value doesn't matter. We reject that. means the only valid solution is 6 hours. Yeah? X, which is the time it takes for the large pipe to fill alone, this equals 6 hours. And thus we are done. Yes. Okay. And so there is our combined rates problem. So I think that's pretty good. I know that that's a long video. Thanks for bearing with me. But I hope that these practice problems worked out give you some insight as to how you're approaching these, because I know that they're not easy. You know, the homework that I've given you for 7.6 is lengthy, and the questions are challenging because they're all quite different. Yeah. Especially the uniform motion problems. So if you're struggling with those, come see me for help. Otherwise, thank you so much for watching. Hope you got something out of it, and I'll see you later. See you in the next one.